Aloha everyone and welcome to our water turbine project proposal presentation. My name is Wong and my intended major is civil engineering.
Aloha, my name is Century Hoku Carter and my intended major is civil engineering.
Aloha everybody, my name is Hannah Asano and my intended major is civil engineering.
Hi, I'm Kelsey Deuz and my intended major is mechanical or electrical engineering.
This project is being guided by Kapiolani, our project mentor, and this presentation is being conducted in the term of summer 2020. Here's an overall outline of our presentation today. First, we will begin with an introduction, followed by background motivation, design problem definition, project expectations, research project process, and concluding with our overall future work. For our background, in the year 2015, the state of Hawaii had promised to have a renewable portfolio standard of 100% by 2045, essentially meaning that they aim to have 100% renewable energy consumption by 2045. In conjunction to this, farmers all around the world depend on reliable sources of energy to provide for their farms, with things such as providing for their tools or electric fencing to keep pests out. And luckily for us, there's a common solution for these two problems.
Our overall motivation for the project is to expand operations and clear the site of invasive foliage to plant native plants. We would like to illuminate the main walkways during after hours since most of Kumu'ola Foundation and its volunteers tend to stay after sunset. There is no access to external power sources, which leads Kumu'ola Foundation to use costly gas generators that harm the environment. Therefore, our design problem definition is to design an affordable water turbine based on the various requirements given by stakeholders to generate enough power and electricity. Our mission statement is to develop, design, and manufacture a low-cost water turbine for the Kumu'ola Foundation that is lightweight, compact, and transportable to generate electricity from the low flow rate streams of Wa'aloa and Naniwapo. It will reduce the environmental footprint by providing an environmentally friendly alternative of producing energy and will allow access to electricity without connection to external power sources, such as power lines and generators.
Moving on, we have our stakeholder objectives. The first objective is to be able to power electrical equipment around property. Second is not to disrupt natural landscape. Third is affordability. Fourth is simple and easy maintenance. Fifth is sustainability, and sixth is functionality. Next, we have our project requirements. Objective 1 requirements cover power storage and distribution. Objective 2 requirements cover water temperature and stream quality. Objective 3 requirements cover price and budget, our budget being $1,600 total. Objective 4 requirements cover easy configuration and easy maintenance. Objective 5 requirements cover compatibility with the environment. And finally, Objective 6 requirements cover the overall functionality of the water turbine.
Here is a general overview of our project organization. For myself, I am acting as the project manager, while Kelsey is acting as project archivist, Hoku is acting as systems integrator, and Hannah is acting as fiscal manager. Under our systems integrator, there are two separate major subsystems. First being power generation, which is being conducted by myself and Kelsey, and the structures and sustainability subsystem, which is being monitored by Century and Hannah. To begin with our mechanical subsystem, we had to first consider how we wanted to design our blades. Because of this, we had to also consider the set parameters. First, they had to be easily constructible and be able to maintain a high spin rate in a low flow setting and low head setting. Because of this, we had considered 3 different iterations of turbines: the Kaplan, spiral, and Pelton wheel. The Kaplan turbine worked well in low head settings, but also required a high flow setting. Therefore, we took this consideration out. The Pelton turbine worked best in low flow settings, however, required a high head. Therefore, we took this iteration out. And finally, we chose the spiral turbine because it worked best both in low flow settings and low head settings, thus allowing us to move forward with a certain design. Moving forward, we had chosen a horizontal spiral turbine, which was based upon the golden ratio. Because of this, we had to test several different degree blade types, first being the 15-degree blade type, the 18-degree blade type, the 21-degree blade type, and the 30-degree blade type. Out of the 4 tested, the 30-degree blade type produced the most amount of torque in the given conditions, thus allowing us to produce the most amount of power with this type of blade. And as you can see at the bottom, we have our 4 different tested blades, plus another 3-bladed axial type. And as you can see, we have our 30-degree blade type highlighted in red.
This is a graph of the recorded daily discharge provided by the USGS of the MANOA stream in the past year. Note that the MANOA stream is a low flow rate stream, and the fluctuations in the graph allow for us to forecast the type of conditions that the water turbine will have to undergo in order to provide electricity. According to the USGS, the stream hasn't really seen a flow rate much lower than the one shown in the graph in the past 9 years. So at a low point of approximately 2.5 cubic feet per second, the water turbine must be able to provide electricity. Any lower than that, the water turbine will not be able to function due to the fact that this is already a low flow rate stream, and any lower, there won't be much water to produce the magnitude of electricity needed. In the event that the stream is at or above approximately 160 cubic feet per second, the turbine should be able to withstand those conditions without overcharging the generator and causing a surge in the system. Over the years, the stream conditions may change and will be in need of reevaluation or possible relocation.
So using the parameters given to us by that USGS website, we were able to use this equation to find a power output for our water turbine. So we found at the lowest rate or lowest flow rate from the USGS website that our water turbine would still be able to produce a minimum of 2,000 watts. We also found that the average maximum number of watts needed for LED lights was around 80 watts. Therefore, even at the lowest flow rate of the stream, we would still be able to power at least 25 lights. Next, we have a circuit diagram, which shows how we go from a water turbine to being able to power lights. So from the water turbine, we go to a generator, then a battery, then an inverter, and next a power distributor, and finally the lights.
So the limitations of this project are social distancing, cavitation, chemicals, heat, noise pollution, and vibrations. For our first point, social distancing, it has prevented us from collecting any data to perform any experiments. The other variables in this project, cavitation, chemicals, heat, noise pollution, and vibrations, are all caused by natural effects by either the turbine's performances or environmental occurrences. And for those of you who may not know, cavitation happens when there are rapid changes in pressure in a liquid and small vapor-filled cavities or bubbles form where the pressure is relatively low. And so when these bubbles pop, it creates a crater-like hole as shown in this figure 11. And this could cause the performance of the turbine to be negatively affected, and other possible outcomes of a popping bubble would be what's listed below. So for our budget overview, it consists of 3 separate subsystems: mechanical, electrical, and civil. And with that, if we take a look at our grand total on the bottom right, it adds up to be $871.94. And that is below the provided budget, which is $1,600.
Here's an overview of our Gantt chart for our project. It is broken off into 4 major subsystems. The first being electrical subsystem, second mechanical subsystem, third civil subsystem, and finally our deliverables/general. Our deliverables/general subsystem had applied to all the previous 3. Therefore, we had decided to claim it as its own area. As you can see here, we're currently in week 10, or we have concluded week 10, and we're hoping to continue working on this if possible.
In the future, we hope to have groups do in-person site visits to Kumuola Foundation because due to social distancing, our group was unable to collect any data from the actual site and instead had to gather information from online sources. And so we would also like groups to further their research on the Hawaiian culture so that they could integrate the traditions into our New World traditions. And that would in turn relate to looking at sustainability through a Kanaka lens. As of now, Hawaii is trying to find ways to be able to survive off of Hawaii products instead of imported products. And we can see through our Hawaiian history that our kupuna were able to achieve this act. And Olelo no Eau by Gary Kaha Ho'omalu Kanata states, Kana'awao o nā kupuna, kalama e ho'omalama lama I keala no nā keiki. And this translates to, the wisdom of the elders is the torch that enlightens the path of the children. And another Olelo no Eau by Mary Kavena Pukui, it states, E lawe I ke a'o a mā lama a e oi mau kana'oau. And this translates to, he who takes his teachings and applies them increases his knowledge. And so these Olelo no Eau could spark ideas on how to build and better design this water turbine while also creating a sustainable environment for the Hawaiian culture to flourish. And before we conclude our presentation, we would like to acknowledge our sponsors, U.S. Department of Education and HEI Charitable Funds, our partner, Kumuola Foundation, our NSIP staff, Kayaka Kepa-Alama, our project mentor, Kelly Ching, Jillian Kamakaila Paulino, Jordan Maeda, Mallory Hataishi, and Casey Wandasan, and finally, the University of Hawaii at MANOA College of Engineering.
Thank you again, everyone for watching our presentation. And if there are any comments or questions regarding our presentation or regarding our work that we've done for this project, please list them in the comment section below. And thank you again.